Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking a little bit more about radioactivity. Specifically, I'm going to be talking about radioactive decay rates, half-lives, activity, that sort of thing. So stay tuned. You'll recall that in my previous video about radioactivity I discussed different types of radioactive decays and basically different types of radioactive emissions. So some possible radioactive emissions include the alpha decay, which is when the nucleus emits from itself a helium nucleus and therefore is reduced by 2 neutrons and 2 protons. So specifically the alpha particle is the helium with the 4 particles, nucleons to it. So this is the same as an alpha particle. There is the beta decay, in which, or sometimes called the beta minus decay, in which the nucleus emits an electron, which is a beta particle or beta minus particle, as well as an antineutrino, an electron antineutrino, which is sometimes represented by a nu with a bar over it. And in this case, the Z value of the nucleus increases 1 because essentially a neutron converts to a proton. The third type that we discussed was the gamma emission, in which the nucleus emits a very high energy photon called a gamma ray and relaxes to a lower energy state. Now there are, of course, other types of radioactivity. For example, a neutron can be released. That often happens in fusion reactions. So for example, you may have 2 hydrogen nuclei. Maybe you have a hydrogen and a tritium, which is hydrogen and 2 neutrons attached, and they fuse together to make helium, or more often really it's going to be a deuterium, that's hydrogen with 2 particles, a neutron and a proton, and it fuses with a tritium, hydrogen that has a proton and 2 neutrons. The result is that you get a helium atom, which has 2 of each, 2 protons, 2 neutrons, and 1 spare neutron, which is released with some kinetic energy, like a 14 or so MeVs, mega EVs of kinetic energy. So that's a fusion reaction. You can also get fission reactions, and that's where you have a large nucleus which splits into 2 smaller ones and maybe a spare neutron or spare alpha particle or what have you. So these are the different types of radioactive decay types and or nuclear reaction types that can release radioactive materials, that can release these decay materials. Today, again focusing predominantly on the 3 that we've discussed, I wanted to talk about radioactivity a little bit more, basically by looking at things like decay rates and how active is a decay, that kind of thing. The basic equation which governs radioactive decay is a rate equation. That means that it can relate the number of nuclei present of a given specimen, the rate change of that number. So this would be the rate change of the number of nuclei present, and it generally is equal to some constant. We might use a lambda or a mu, times the number of nuclei that are actually present. And this rate at which the decays are occurring, various sources will call it a positive rate or a negative rate. I like to make it a negative rate because essentially what's happening is that the total number is being reduced, and that sets up a better equation because this equation is very similar to some other ones that we've seen previously this semester. You may recall that for an RC circuit, which is discharging, so the capacitor is discharging through the resistor, that the charge on the capacitor is related back to the current that is being used to discharge it, or the current is related to the charge, basically by using the Kirchhoff loop rule. And so what you end up with is that the current, I times R, is equal to negative of the charge divided by the capacitance, or in other words, that I is equal to Q over RC. And this right here we represented by noting that I is the rate change of the charge. So delta Q over delta T was equal to 1 over tau times Q. And so this 1 over tau term here is very similar to the lambda term that I included in this equation up here, where Q can be related more or less to N, and the delta Q over delta T can be related to delta N over delta T. We also had the LR circuit, and for the LR circuit we got a similar result, except for that it was in terms of the charge, in terms of the current rather than the charge. And so for that one, what we ended up with was delta I over delta T was proportional to the current I with a 1 over tau factor, where in this case the tau factor is the inductance divided by the resistance of the system. So once again we have a tau which is similar to the tau that we had here. We have an I which is similar to Q, which is similar to N. We had a delta I over delta N, which is similar to delta N over delta T. So therefore we expect our solution here to be similar as well. What we expect is that the number of nuclei remaining should be whatever our starting number was, N naught, times e to the negative, and this would be like a t over tau, but our 1 over tau is just equivalent to lambda, so we could write e to the negative lambda t. So this right here gives us correctly the number of nuclei remaining after a given time given the initial number of nuclei. So this equation should behave similarly to the ones that predicted the RC circuit and the RL circuit. We would expect, therefore, if we were to make a graph in time, so here's time, here's the number of remaining nuclei, we'd basically get this exponential decay. And this one right here would represent N naught. At time t equals 1 over lambda, we get a value here of 1 over e times N naught for our N. After 2 of these, so in other words, if I come out to here, this is 2 over lambda. This right here should be 1 over e squared N naught, etc. Now there's another thing to note, which is that when I introduced over here delta N over delta T, delta N over delta T, which is the rate at which the nuclei are decaying, is also called the activity. So this represents the activity of the sample. And if you think about that definition, it should make some sense, because each time that you change the number of remaining nuclei, that basically means you've lost one nucleus. That required an emission to have happened, and that is your activity. So each time you lose one nucleus, you're also getting one emission, and so the more rapidly you're losing nuclei, the more rapidly you're getting emissions, and therefore the more emissions you would detect in a given time. There's another term that you may hear with nuclear decays. It's called the half-life. We've also encountered that before in these lectures, because it was mentioned when talking about RC circuits and LR circuits. That is the half-life. I've been using T1/2. Some people like to use a capital T for here, and it is related to that lambda fact. Specifically, the half-life is equal to the natural log of 2 divided by lambda. So what is the half-life telling us? Well, it's basically telling us how much time will elapse before we've reduced from our starting number of nuclei to half that number. It's worth noting that if we have a little stopwatch and we were able to time this, and we timed one half-life, and then we hit pause and reset it and then restarted it, that after one more half-life, it's sort of like we've reset the number to a new value of n naught, and so after one more half-life, we'll be at another half of that new n naught, which is a quarter of our n value. So after, let's say, m half-lives, n will equal 1/2 raised to the power of m times our original number. So worth noting that. Graphically, if we have a number of nuclei here and a time here, and we again draw out our little exponential curve. It's not a very good exponential curve. My pen is slipping a little more than I'd like it to here. I cannot draw to save my life. Graphically, we get something that looks like this, where after half of a half-life, after one half-life, we have half of the initial sample. After 2 half-lives, we have a quarter of the initial sample. After 3 half-lives, we have 1/8 of the initial sample, etc. Now, the activity of the sample is the rate change of the sample's nuclei count, and so therefore it's also the rate at which emissions are occurring. So if we are doing alpha decays, then this is the rate of decay. It means also how many alpha particles are being emitted from the sample per second. Now, there are 2 common units used. The first common unit is the Curie, abbreviated CI. It's named after Madame Curie, and I guess you could argue after her husband, Pierre, with whom she shared one of her Nobel Prizes. The Curie basically represents about 3.70 times 10 to the 10 decays per second, and therefore that many particles emitted per second. The SI unit is called the becquerel, abbreviated BQ, and it represents 1 decay per second, ergo 1 emission per second. This also incidentally means that 1 Curie is equal to 3.7 times 10 to the 10 becquerels. And I guess if we want to do with sig figs, 1.00 Curie is 3.70 times 10 to the 10 becquerels. One application of radioactive decays and decay rates and so on is that we can know what a half-life is for various common elements by sort of observing the rate at which they decay. And then we can go and look at what fraction of that element is in this radioactive form or not. So for example, like you've heard of carbon-14 dating, or even carbon-16 dating. And essentially what happens is the carbon atoms decay at a given rate. And so if you look at a sample of something that should have carbon atoms in it, an older sample will tend to have less of these carbon-14, carbon-16, etc., than, say, a newer sample. And so you can date things that are a few thousand years old, up to maybe tens of thousands or even possibly hundreds of thousands of years old, using carbon. For older samples, you need some other element like uranium, but you can look at the amount of, let's say, carbon-14 present in a sample and determine therefore what that sample's age is reasonably well by seeing, okay, in order for it to have this fraction of carbon-14, let's say, then this many half-lives must have passed, and we know that the half-life is so long. For carbon-14, for example, the activity in like currently in the atmosphere, for example, is somewhere in the neighborhood of a little more than 1/4 of a becquerel per gram. Okay, so if you have a sample whose activity is 1/4 of this, let's say, then that means that it's gone through 2 half-lives worth of decay. And so then the half-life of carbon-14 is a bit over 5,700 years. So if you have a sample which per gram of your carbon presence has an activity of 1/4 of whatever the current value is, 1/4 of that 0.255 becquerel, then the implication is that 2 half-lives have passed for that sample. So that sample would be 2 times this number old, or basically 11,460 years. Okay, so that's how carbon-14 dating works. And again, you can get to maybe on the order of 100,000 years, a few 100,000 years, maybe, with your carbon-14 dating. It also depends a bit on things like how big is the sample that you're trying to date, and how good are your detectors and so on. For things that are older still, millions of years old, billions, etc., you need some other element like uranium that has a different half-life. Let's do a slightly longer example. So we have a certain radioactive sample. It has a known mass of 1 kilogram. Initially, it's pure. That means we have 1 kilogram of just this substance. And then we want to know, given a decay constant of 50 per second, what time will its mass be 100 grams? All right, so what time will the mass fall to 100 grams? Well, essentially, we may look at this and say, all right, how do you get that from this set of information? Well, remember that the number is also given by, or that the number can be related to mass and vice versa via the molar mass. And the molar mass is some fixed constant. Well, okay, the molar mass and Avogadro's number, those are both fixed constants for a given sample. So the equation for the mass should follow the same basic equation as for the number present. So my rate at which my mass is decaying, delta M over delta T, should look like lambda times M, where this right here is my lambda in question, and therefore my mass should look like whatever my initial mass is times e to the negative lambda t. So now we just have to figure out what these represent. This would be my initial mass. This right here would be my mass at that time. And this right here would be my lambda value. So I should be able to basically solve. I have e to the negative lambda t is equal to m over m naught. And so that is 0.1 grams divided by kilograms, excuse me, divided by 1.0 kilograms, which is just 1/10. And so negative lambda t is equal to the natural log of 1/10, or in other words, t is equal to the natural log of 10 divided by lambda. Alright, so we would just take the natural log of 10, so 10 ln, which is 2.3, and then we have to divide that by this rate of decay. Now, we are kind of assuming that this rate of decay is pertinent to the mass equation and not to the numbers equation. You know, if I have 50 decays per second, then that's not going to be the relevant number to use here. And so this, maybe is something like this rather than total decays per second, in which case I'd need to use an Avogadro's number and a density to get to my value. This right here, as it turns out, is about 0.0461 seconds. So after a little under 5 milliseconds, we will, in this case, have reduced our sample from our initial 1 kilogram down to our final of 100 grams. So that's all for the video for today. Hopefully you've learned something from it. As always, thanks for watching.